name's Seb Spain. I'm a lecturer in polymer chemistry in the department. My research group is quite varied. Our main interests are in the development of materials for drug delivery and therapeutics, but we also do some research into materials for coatings, for example with paint companies. We do a considerable amount of small molecule organic synthesis. We're not going to be claiming that we're proper organic synthetic chemists. We do a lot of polymerization techniques, particularly living polymerizations, so controlled relative polymerizations. But we also, because we're on that boundary between chemistry and biology, we also spend a lot of time doing tissue culture, so growing cells. One of my students is currently growing tissue engineered skin, so they take bits of skin from donors, remove all the cells, and then start growing, regrowing it to allow a consistent model. So we use a very wide range of techniques. So what's really taken off in the last 20 years is how precisely we can make a polymer. So the classic polymer chemistry theory of the last 50 years is we've been considered the bucket chemistry, just throw it all in, heat it and hope. We've got a lot better at making precisely controlled polymers, so we can make block, 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 block. We're now getting much better at doing almost sequence control, so it's much more like a protein or DNA where we want exactly this sequence of material. And that is really starting to take off in the last 5 years, and I think in the next 20 we'll be able to. We won't be mimicking nature. We're never going to get quite that good, but we'll be much closer than we are now.
What can you tell us about your research into stimuli responsive materials?
So a stimuli responsive material is one that has a sort of abnormal response to an external stimulus. So the classic example is if you think about making a cup of tea and you stir your tea and you put sugar in it. The hotter the tea is, the easier it is to dissolve the sugar. Whereas the polymers that we tend to work with is if you heat them up, they become insoluble, which is sort of the opposite response to what most people think. And so the way that we use that, one example is that we can take a particle, so we have a plastic particle fundamentally, which on the outside is a hydrophilic coat, and that coat helps basically the particles circulate through the bloodstream. And because they're particles and quite big, they then localise in tumours, which tend to be slightly hotter than the rest of the tissue. And when the temperature gets high enough, that hydrophilic coat collapses, becomes hydrophobic, and that allows it to get into the cell. So our particular focus at the moment is in trying to target the immune system. So if you think about particular diseases, things like multiple sclerosis, these diseases are diseases of the immune system, so it's your immune system attacking itself. And at the moment the drugs are very poor, and so what we're trying to do is now develop materials that can target the specific biochemical environments found in those sort of diseases. So it will basically allow us to target much more accurately to the disease site rather than have to give people a drug that will basically give them lots of side effects. So hopefully it will be a much better response. So my background has always been polymer chemistry. As long as I can remember, Sheffield has been an absolute pioneer in polymer chemistry. They've had an incredibly strong background, Professor Ryan and Professor Arms particularly, but also across the wider universities, so in physics and engineering we have very, very strong polymer science. So for me it was somewhere where my research fitted well, and because I could collaborate with a lot of people. We collaborate within the university. We collaborate with the dental school, Professor Paul Hatton there, so we do materials for regenerative medicine for teeth. We work with Professor Sheila McNeil in materials science, where we make materials for skin regeneration. Within chemistry, we work a lot with Sasha Mikhailuk, looking at how these things behave in solution. In terms of outside the university, we collaborate strongly with industry. We have links to a lot of companies. Internationally, we work with a group in Brisbane. We've worked quite widely across the world.